Okay, so this is a question that came up in the homework. It says a golfer stands 435 feet horizontally from the hole and 55 feet above the hole, as shown in the picture. If the ball is struck and leaves the ground at an initial angle of 30 degrees with the horizontal, then with what initial speed should it be hit to land in the hole? Okay, so again, it's a very nice picture, but I'm going to try to draw another one here. So probably looks more like this. So down here is the hole. Up here is the golfer. We know that this is, boy, I can't do vertical lines here, sorry. So this is 435 feet horizontally to the hole, and then 55 feet above the hole. And this is the horizontal. So the idea being, we're going to strike the ball at 30 degrees to the horizontal, roughly like that. And hopefully it'll land in the hole. And the question is just asking for with what initial speed, we'll call it V0, we need to hit the ball in order to make that happen, right? To get a hole in one, essentially. Right, so we're not going to change the angle. The angle is 30 degrees. And so we just need our equations for projectiles. So this is for projectile motion. And it's on your formula sheet. So this is the position function, the position of a projectile. Okay, so the x component is just x0 plus v0t times cosine of theta. And then the y component will be y0 plus v0t times the sine of theta minus 1/2 gt squared. Okay, so g is the acceleration due to gravity, and since this is in feet, distances are in feet, right, we'll use the 32 feet per second squared as our value for g. Theta is also given. It's 30 degrees. And so x0 is the horizontal starting point. We might as well just call that 0. But y0 is 55 feet above the ground. So y0 will be 55. Right. So let's plug in our numbers and get our specific position function here. So again, x0 is 0. We don't know what v0 is, so that's our variable. And we don't know what t is. T is essentially how long it takes, right, to get into the hole after it was struck. All right, so y0 is 55. Again, v0 we don't know, t we don't know. Sine of theta, we know theta is 30 degrees. And then 1/2 times g, 1/2 times 32 is 16 times t squared. Okay. So that's our position vector, right? And, you know, we can split this up into the components, right? The x component is just v0 times t times the cosine of 30 degrees. Well, all right, so cosine of 30 degrees is the square root of 3 over 2. And then the y component will be, let's put the negative 16t squared first, plus v0 times t times the sine of 30 degrees. Sine of 30 degrees is 1/2. And then plus 55. Okay. So this essentially will be the position of the ball at any time, at any point along its path after a time t. So think about where we want the ball to end up. We want the ball to end up in the hole where x is 0. Oh, I'm sorry. X is 435. That's the horizontal distance, 435 feet. And y is 0, right? Because it's at ground level here. Again, we're starting on top of the hill that's 55 feet above the ground. So that's our initial height, 55 feet. And then the hole is at 0 height, at the bottom of the hill. Okay. So I suppose the next thing to do would be to set x equal to 435. So v0 times t times the square root of 3 over 2 is equal to 435 feet. And then the y, so negative 16t squared plus 1/2 v0t plus 55. That should be 0. And yep, this gives us two equations. But we also have two variables, v0 and t. And the question is asking for the velocity. We don't care how long it takes. We don't care about the time. So I would try to eliminate t. I would eliminate the time t from the two equations. So if we solve this equation for t and plug that into the second equation, that should give us an equation for v0. Okay. So to solve for t, multiply by 2 and divide by v0 square root of 3. So 2 times 435 divided by v0 times the square root of 3. And by my calculation, I hope this is right, it's 870 divided by v0 square root of 3. So if that's t, we can substitute for t 870 over v0 square root of 3 into the second equation here. Right. So when that happens, this equation becomes in fact, I'll write it way over here. So negative 16 times t squared. T is 870 over v0 square root of 3. And then square the whole thing. Plus 1/2 times v0, so v0 over 2 times 870 over v0 square root of 3. Plus 55 equals 0. So having eliminated t, we should be able to get v0 at this point. It's just a matter of a little bit of algebra here. So 870 squared is 756,900 times 16. So this is going to be a pretty big number here. This is negative 12,110,400, all divided by v0 squared times 3. And so if you divide by 3, we get negative 4,036,800, all divided by v0 squared. Okay, so that's the first term. For the second term, it looks like the v0s actually cancel. Yep, because v0 is in the denominator of t. Okay, just making sure. And then we have 870 divided by 2, which is the original 435 again. So this is 435 divided by the square root of 3 plus 55 equals 0. And yeah, I'll just bring all this down. Okay. So this is an equation in V0. I think we'll just subtract everything on both sides here. So they're both going to be negative, right? So 4,036,800 divided by V0 squared. That's all going to equal 55 plus 435 over the square root of 3. And I know it doesn't say in the question, I think they wanted us to round to 2 or 3 decimal places. Well, actually it says do not round your final answer, round to the nearest tenth. Okay, so we're not going to round here. Fair enough. I guess what we can do is get a common denominator, right? Multiply this by root 3 over root 3. So this is 55 square root of 3 plus 435 all over the square root of 3. Right? And now we can just cross multiply. Square root of 3 plus 435 all over square root of 3. So, yep, we'll just cross multiply. And that gives us 55 square root of 3 plus 435 all times v naught squared. And that's going to equal the square root of 3 times, well, I'll put the number in front of the square root of 3, 4,036,800 times the square root of 3. And that's a 3 there too. Okay, so now just divide by everything that's not V0. That's the 55 root 3 plus 435. Right, so these cancel, and that's not V0, but the square of it. Right, so we'll just take the square root of all of that. So 4,036,800 square root of 3 over 55 square root of 3 plus 435. Yeah, so that's V0 itself. Right. So kind of a mess, but this is sometimes happens. This should be the exact answer. And now just plug it all in your calculator to get the approximate answer, and I guess we'll round to the nearest tenth. Yeah, again, so be careful how you put this in your calculator, especially if you're using a graphing calculator. You make sure that all your order of operations is good here. I mean, essentially, it'll look like the square root of 4,036,800, and then another square root of 3, close parentheses, and then the square root should be over, divided by another parentheses. I would do 435 plus 55 square root of 3, close that parentheses, and then when you hit enter, I get approximately 114.829467, blah, blah, blah. So to the nearest tenth, it would be 114.8. And let's see, this is a velocity. We were in feet. and time should be in seconds here. So 114.8 feet per second. And I just want to check. I think that's the answer they wanted. So I hope this helps. Again, it's kind of a confusing problem. It helps to draw the picture. And again, I just used the position function for any projectile motion, plugging in our specific numbers, and then essentially solving a system of two equations in two variables here. It is a nonlinear system, and so I think by just substitution here, right, solving this for t, and then plugging that into the second equation, right, so this value got plugged in here and here. And the rest is just doing the arithmetic and very carefully. It is easy to mess that up. So, but I think that's the answer they want. And again, if they ever want the exact answer, even though it's kind of a mess, you would put in the horrible square root of whatever that is. And there might be ways of simplifying this, but I'm not gonna bother at this point. So to get the approximate answer, you can just plug it all in your calculator, and that should be good enough. Right. So I hope this helps.